Okay, welcome back. Here we go. We're looking at power today, power in electrical circuits. So 5 start questions, pause it, and we're coming back with the answers. If you're unsure of any of these answers, unsure of the concepts, then you must go back and review the previous stuff. Okay. Today's lesson is getting a little bit more technical because it's going to be relying on several areas of physics. So power. Power is from the energy topic, and if you recall, power is all about how fast we can transfer energy. Okay, this is what makes these people powerful, these things powerful. They can transfer energy very quickly, or do stuff very quickly, do work very quickly. Okay. And in physics, power is defined as the rate of energy transfer. An example here, we've got 2 planes. Obviously the one at the top there is more powerful than the old-fashioned one at the bottom. That's because it can deliver energy much quicker. It can transfer energy much quicker. It can do work at a faster rate. That's what we mean by power. And from the energy topic, here are our formulas. If you are unsure, do go back and review that lesson, okay? Because we're focusing on power in electrical circuits today. So there are 2 equations we can use. One is P is equal to VI, and the other is equal to I squared R. And very simply, the one on the left, this first equation, tells you about the power that is delivered to components in a circuit. The one on the right tells you how power is dissipated in a circuit. Okay? And you should also know the quantities, symbols and units. So pause this and write this down. This is the keynotes. And moving on. So using the 2 formulas, here's an example of the first one. Basic setup, measuring current and voltage, and we can see that in the text here that we've got a voltage and a current measurement. Okay? We want to know the power that's being delivered to this circuit. We simply apply the formula, put the numbers in, and get an answer of 1 watt, or 1 joule per second. Okay. Second one, how much energy is being dissipated by this resistor? Remember that a resistor will dissipate energy as heat. And we're looking at the rate that it's been dissipated. We know the current, we know the resistance, and so we use the second formula, which gives us a value of 120 watts, which is about right for a resistor. Okay. Pause that and write these examples down if you need to. I am moving on now. Okay, so here's a real problem with a kettle, and a kettle plugged into the mains, and we've got a power rating there. So these are our 4 questions. First one being, how much current does it draw? How much current does the kettle take when it's being used? That's a simple application of power is voltage times current. Put our numbers in, or rather rearrange it because we're looking for the current, and then we get an answer of 9.6 amps. Therefore, we're going to need a 10 amp fuse. Third one, what is the resistance of the kettle? Now, we want the power formula that involves resistance and current and power. We rearrange it, and we get a value of about 24 ohms. And that's about typical for a kettle. We leave it on for 2 minutes. We know from energy topic that power is energy over time. What energy is power times time? And so that kettle uses that amount of energy, 264,000 joules or 264 kilojoules. Take a pause and copy that down. Unpausing. So here's the second one involving a cooker that's plugged into the mains. So when all the hobs are on, we know it's drawing a certain amount of current. And we're going to be asked about the current that it draws, and we're also going to be asked about the resistance of one of the hobs, and also another one about how much current it takes. So let's look at this one, let's unpack this. So the first question is a simple application of the power formula to get 5.75 kilowatts, 5,750 watts. The second question, we need to know resistance. So we're using the second form of the relationship, and we need to rearrange it to make our subject, and then we can pop our numbers in and get an answer of 20 ohms, which is a typical value. The third one is asking us to find a current. Now we know that it takes 1,000 joules per second, which is 1,000 watts, that's its power. And so we apply the formula, and this time rearrange it to make current the subject, which involves rearranging it to make I squared the subject and then square rooting the whole lot. Okay, so slightly more complex. Notice in each time when I write these equations, when I solve these problems, rather, I write the equation, show them working out, put the numbers with a unit. Now pause this. And we're going to move on. So you will find a Word doc with these questions in. There are 6 questions, and they get a little bit more tricky as they go along. So have a look in the document resource if it's there. If it's not, these are the first 3 on the screen, so you can pause the screen and start on those. These are questions 4, 5 and 6. Pause the screen if you haven't got the document. I'm going to now move on to the answers. So 1 and 2, straightforward application, number 1. And then if we look at number 2, notice I've put the answer in kilowatts there because it looks nicer, 2.3 kilowatts. You could get that's correct as well. The resistance question, what is the resistance of the kettle? Notice I could have used either that formula, our power formula, or I could have gone back to our lesson on Ohm's law because I know that V equals IR, and you'll note that they both get the same answer because they are both consistent with each other. Okay? So there were 2 ways of getting that final solution there, and I've shown you both there. 3 and 4. 3 is a straightforward application. Number 4, nothing challenging there. Notice that we get a voltage of 110 volts for this one. So I'm guessing that that toaster comes from America, which will use a different voltage supply to us. And we get a resistance of 22 ohms, which is typical for that sort of heating resistance. Okay. Now the 2 tricky ones, or rather number 5 first of all, I do apologise. Straightforward application, first one. Second one we rearrange to make R the subject. And the third one we're asked to find the energy. How much energy does it use every hour, rather? So we know the energy being supplied is 3,400 joules per second. And we multiply it by an hour. Now what's gone on here? How much energy does it use every hour when it's on? Okay. This calculation here is wrong. So I'm going to correct that now as we do it on the screen. I do apologise. Gosh, how did that one slip through the net there? That's number, that one there. So, how do I change that? Okay, so as we do this, let's just picture tools. Let's crop. Let's disappear that. Okay, and let's put the correct answer in there, folks. Insert, and let's insert a text box. So how much energy does it use per hour? Well, it uses 3,400 joules per second. Joules per second times by an hour, 60 seconds, times by 60 minutes, which equals that. And then we can do that on our calculator. 3,400 times by 3,600 gives me 1224000 joules, okay, which is quite a lot of energy. In fact, we could write that into megajoules could we? 1, 2, 3, 1, 2, 3. We could write that into megajoules, millions of joules if we wanted to. Okay, I'm going to move on. And the final question, notice that we've got these difficult figures here, so I turn them into standard form, and we get an answer here of 0.0060. Okay. So the challenge here is dealing with these tricky numbers, turning these into standard form. Okay, so pause that if you want to get the correct answers. Any issues, get me on Teams. But we'll go to the final thing. So why do we actually use AC to transmit power? And the reason is because when the voltage is stepped up, the current is stepped down. And we know that power dissipation is proportional to the current squared, because P equals I squared R. So the smaller we can get the current, the smaller we can get the power dissipated. Okay. Right then, that's quite a difficult lesson. It's all higher tier stuff. Have a go at the questions, and I will see you at some point in the future.